Hello everybody, welcome back again. Here in this video we will study about the design of guide bank. Okay, and you can say designing of bell bond. So in this video we will first see the design steps of the guide bank. Okay, and after that we will also do a numerical related to designing of guide bank. Okay, and this is the question over here, and we will solve this numerical. Okay, and before solving this numerical, let's see the design steps, different design steps that we should follow during the designing of guide bank or bell bond. Okay, so basically we have to follow 4 different steps for determining of for the design of guide bank. Okay, so let's see first what is guide bank. So you can see here in this figure. Okay, this is the typical cross section of guide bank. Okay, and here in the side you can see here this is the lining. Okay, and this is provided with boulders, or you can say concreting. Okay, why we provide this guide bank? Because for the protection from the scoring. Okay, we have to provide this guide bank of the guide bank. So you can see here the guide bank, this is also called bell bond. Okay, and guide banks are made for guiding the stem near a structure so as to confine it in a reasonable width of a river. Okay, and this is also called bell bond. And as I already said, this guide are especially provided for the guiding the stem near a structure so as to confine it in a reasonable width of a river, and keeping the safe from the scoring of the soil. Okay, it's near that point. And the guide bank are other work embankment for guiding the flood water of a river near a structure constructed across the river. Okay, and you can see the 3D figure of guide bank. You can see here. Okay, and now let's see the design steps of guide bank. So in very first step we have to design a bridge all over a river, or you can say simply a minimum width of waterway. Okay, for this we use Lacey's Resime waterway theory, or you can say the clear waterway. This can be calculated. That is the value of P equal to 4.75 root under Q. Okay, this formula is taken from the Lacey's Resime theory. Okay, and the width of channel, that is the value of P equal to 4.75 root under Q. And for the length of this we have to increase this value with the 20%. Okay, and after the increasing this value with 20%, we get the value of L, and simply we can calculate the value of L equal to 1.2 times of this value P. Okay, and we get the value of L. Okay, and after first step, let's see the second step. Okay, in this step we have to determine the length of upstream guide bank, and for this we can simply use this formula 1.25 to 1.5 L. Okay, so this is the criteria for the length of upstream side of guide bank, and you can take this value between this. Okay, 1.25 L to 1.5 L, and length of downstream guide bank equal to 0.25 L. Okay, and let's assume the upstream curve head equal to 120 degree to 145 degree. You can see here in this figure. First see the length of our upstream guide bank. You can see here in this video, this is the upstream curve head and this is the downstream of the curve head. This is the typical example of guide bank, or you can say bell bond. Okay, and these two is provided here, this in the upstream curve head, and you can also see these two in the downstream side. Okay, and for the upstream we have to take this length equal to 0.45 L, as we discussed here, 0.25 to 1.5 L. Okay, and length of downstream guide bank, that is taken 0.25 L. Okay, so this value is taken 0.25 L as we discussed, and the assume upstream curve heads equal to 120 degree to 145 degree. You have to take the value of upstream curve head, that is the angle of this angle. Okay, you can take this angle between the 120 degree to 145 degree. Okay, as your choice, you can take any value between this. Okay, and for the downstream curve head, you can see here this is the downstream curve. Okay, and for the downstream curve we have to take the value angle downstream curve head equal to 45 to 60 degree. This angle you can see here, this angle you can take between the range 45 to 60 degree for the downstream curve. And now for the radius of upstream curve, this is the value of radius, simply r equal to 0.45 L. You can see here this is the radius for the upstream curve. This is radius equal to 0.45 L, and the radius of downstream curve head r equal to 0.25 L. So we have to take this value for the downstream. And in step number 3, cross section of guide bank. For the cross section of guide bank, we will provide free body equal to 1.25 to 1.5 meter, and side slope we take 2.1. you can see here, this is the side slope, and this value is generally taken 2:1. Okay, and now top width of a top width, or you can say carriageway, this generally taken 5 meter. Okay, and this is not less than 4 meter, means we have to take top width is greater than 4 meter, and generally we prefer 5 meter. Okay, and you can see here this is the top width of guide bank, and this is generally taken 5 meter. Okay, and slope is 2.1. So this is all about the third step. Now in fourth step. Okay, fourth step we have to design of stone pitching and Operon. For this we simply use, for the slope pitching thickness we use T equal to 0.06 into q to the power 1/3, and this value is simply denoted by a small t. You can see here the slope pitching thickness. Slope pitching thickness means this is the slope, and the thickness of this slope pitching, you can see here this distance is taken a small t, and a small t equal to 0.06 q to the power 1/3, and q is given in the question, and after using discharge we get value of a small t, and after that we have to determine thickness of Operon, and this is denoted by capital T, and capital T simply calculated by 1.9 times of a small t, and a small t value is taken from here. Okay, and after that we have to calculate length of Operon, and length of Operon can be calculated equal to 1.5 d. Okay, and now you have to understand what is d. Okay, and simply d can be calculated equal to 1.2 times of r minus 1 for the straight ridge guide bank, and whenever we provide for curvilinear transition portion, we have to use this d value equal to 1.5 r minus y. Okay, and now you have to know what is r and y. So you can see here this is the y equal to nothing, it is just a depth of water above the river bed level. Okay, you can say in this cross sectional guide bank, this is the y. Okay, and y is the depth of water above the bed level. From this is the bed level, this is the depth of water from bed level to the this level. This level is called high fluid level. Okay, and from the distance this is y, depth of water above the bed level. Okay, and after knowing this value we have to calculate value of r. Okay, and R can be calculated with the Resime formula, R equal to 0.47 root under R equal to 0.47 into QF Q by F to the power 1 by 3. Okay, so this is just a bracket. So for 0.47 into QF to the power 1 by 3. Okay, and here this is also unknown, that is the factor, and the F is the silt factor. We already done different numerical related to silt factor, and if the in question if silt factor is given, then we have to use that value. If there is not given silt factor, if there is provided diameter of silt particle, then we have to calculate this silt factor, and for the calculating this silt factor we use this formula, silt factor F equal to 1.76 root under D, and where D is the diameter of silt particle in mm. Okay, and after calculating this value of F is unknown, and for this formula now we calculate the value of R. Okay, and after calculating R we can simply calculate the value of D equal to 1.25 R minus 1 for the state rich Grad bank, and D equal to 1.5 R minus Y for the curve linear transition portion. Okay, and when we use this or when we use this, okay, this depends on according to the question. Whenever in the question sets provide a state rich Grad bank, then we have to use this formula, and whenever in question said for the curve linear transition, we have to use this formula, and if in the question not mentioned, then we have to provide this both. Okay, we have to provide this both, and after this, then you can use this formula too, and using this value of D, two different value, we have to calculate length of Operon, also two value. Okay, this is all about the designing of stone pitching and Operon. Okay, and by the using this fourth design criteria, we can simply design the Grad bank. Okay, and let's see one different topic here. This is launching Operon. Okay, in numerical we have given different value of the launching Operon, and this is also asked in short note. Okay, what is launching Operon? So let's see definition of this. Whenever a sloping face is protected by the stone pitching. Okay, this is the stone pitching provided here for the protection of this. Okay, against the score, as I already told, this protect from the scoring. The pitching extended beyond the toe on the bed, and this slope pitching is extended from here. Okay, this is the toe of the this, and this is the toe, and this is extended some distance away from the toe. So this stone pitching is provided in slope also, and some distance from the toe. Okay, till this. So the pitching extended beyond the toe on the bed in form of a packed stone. Okay, in the form of this is packed stone. This is called the launching Operon. Okay, so we already calculated this value, and as I said, the value of length of Operon, that is the value of L equal to 1.5 D. This is the value of this from toe of the from toe to this point. Okay, and this value is 1.5 D. Okay, and value of a small t is calculated equal to 0.06 into q to the power 1 by 3. Okay, and this is the thickness t, and as we see thickness of Operon, that is t, capital T equal to this, and this value is taken 1.9 times of small t, this small t. Okay, and we already discussed about different parameters, and this is the freeboard from HFL, high fluid level, to the top width. This is the freeboard, and simply we provide 1.25 to 1.5 meter as we discussed, and this is the RL, you can say riverbed level. Okay, by the helping of these different four design criteria, we can simply design the Grad bank of the Grad bank, and simply you can say bell bond. Okay, Now let's see the numerical related to this. We have numerical given over here. Design and sketch a grad bank including launching Operon. Maximum discharge is 10,000 cubic decimeter cube per second. HFL, that is high fluid level, equal to 250 meter. River bed level 242 meter. River bed material average size, that is the value of D equal to 0.25. So this value given over here, and using this all value we have to design a grad bank. Okay, so now let's see the solution with the help of previous discussed design criteria. We have to design. Okay, so we follow this design criteria one by one. Okay, so before starting the solution of this numerical, if you are new to the channel, please do subscribe the channel and like the video and press the bell icon so you will get regular updates. Okay, and I have uploaded different video related to our civil engineering as well this irrigation engineering and different numerical as well theory. Okay, and I will keep the link of those in description box. You can visit from there. Okay, now let's see the solution. In very first step we have to determine clear waterway, that is the value of P equal to 4.75 root under cube. This value, this formula is given from the Lacey. Okay, and P equal to 4.75 root under cube and Q is given 10,000 cubic. Okay, so this value becomes 475 meter, and for L we have to increase this value with 20% as we discussed in the design criteria first. Okay, you can see here we have to calculate the value of P. Okay, using Lacey's theory. So P equal to 4.75 root under cube, and extra 20% may be provided for the thickness of bridge pier. Okay, you can see this, what is bridge pier in figure. For this we have to increase 20% extra. So L equal to 1.2 times P. That's why we take L equal to 1.2 times of P. So this value becomes 570 meter. Okay, and after this we have second design steps. In this step we have to determine the length of upstream grad bank. Okay, you can see in this figure we have to calculate this upstream length of grad bank, that is 0. You can see this is the upstream of grad bank. Okay, and this value is taken from 1.25 L to 1.5 L, from here to here. Okay, and this value becomes 1.25 L. We take, okay, you can take this value between this range. So 1.25 into L, the value of L is already calculated 570. So this value becomes 712.5 meter. Okay, now length of downstream grad bank. Okay, for this downstream grad bank we have to use this 0.25 L. So 0.25 L equal to 570 meter. After calculating this value we get the downstream length of grad bank equal to 142.5 meter. Okay, so you have to show this value in the figure. Okay, so this is 712.5 and 142. 712.5 and 142.5. Okay, so we have to show this all value in the figure. This figure is also very important for our examination point of view. Okay, in the examination we must provide this figure. Okay, with the different parameter shown in figure. So now we have to upstream curve head equal to 130 degree, simply assume, and downstream curve head equal to 45 degree. Okay, and this range is taken in upstream curve of head is taken 130 in between 120 degree to 145 degree. So we just assume 130 degree, and for the downstream curve head we have to take the angle between 45 to 60, and we just take 45 degree. And now we have to calculate the radius of upstream curve head, and this value equal to 0.45 times L. Okay, as you see here, 0.45 times L, and the value of L is already calculated, that is 570 meter. So we keep this value, then we get radius of upstream curve equal to 256.5 meter, and similarly the radius of downstream curve equal to 0.25 L. So this value becomes 142.5. Okay, now in third step we have to calculate the cross section of grad bank. Okay, and for this we have already given in question, that is the high fluid level equal to 250 meter. You can see here, high fluid level equal to 250 meter. Okay, and this is the high fluid level. Okay, this is high fluid level is given in question, 250 meter. Okay, and let freeboard equal to 1.5 meter. This is the freeboard. We have to provide freeboard between 1.25 to 1.5 meter, as we already discussed in the design criteria. Okay, so the freeboard is taken here 1.5 meter. Okay, and top width equal to 5 meter. As we discussed in design criteria, you can see here freeboard we have to provide between these 1.25 to 1.5, and side slope 2.1, and top width 5 meter. Okay, so for according to design criteria we provide this value. Okay, freeboard 1.5 meter, top width 5 meter, and HFL this is already given in question. Now we have to calculate top level of grad bank. Okay, simply you can calculate this top level of grad bank. Okay, this is top level of grad bank, and this value simply calculated by adding this freeboard in this HFL. Okay, and you can say the value of HFL is given in question 250 plus freeboard. Freeboard we have already assumed 1.5 meter. After adding these two value, this value from here to here, and freeboard from here to here, so we get overall depth. Okay, from here to here, this value becomes top level of grad bank becomes 251.5 meter. Okay, so this top level becomes 251.5 meter. Okay, so we already calculated top level of grad bank. Now we have to design stone pitching and Operon. So depth of water above the bed level, this value depth of water above the bed level, for this y value we can simply calculate this value from subtracting the river bed level, this level minus from HFL minus this level. Okay, after so minus this river bed level we get the value of y. Okay, so y becomes 250 minus 242. Okay, this value is 240, and this bed level is given in question 242. Okay, and after minus this 242 from this value we get the value of this y. Okay, so the value of y becomes 8 meter. Now we have to calculate the height of a bank above the river bed level. Okay, and the height of the bank above the river bed level. Okay, you can see here this is the river bed level. Okay, and now we have to so for this you can see this is the bed level of river. Okay, river bed level, and this is top width, and this value is 251 meter, and this value is 242 meter. Okay, now we have to calculate this value. Okay, and you can see this value is height of bank above the bed river, the height from here to here. For this now we can simply calculate by minus this this is the 242. Okay, and we have to minus this 242 from this value 251 minus 242, then we get distance from this point to this point. Okay, so the height of bank above the river bed equal to 251.5 from here minus 242 at the bed riverbed level. Okay, then we get the value of height of bank equal to 9.5 meter. So this value becomes 9.5 meter. Okay, this is the height of Grad bank. Now we have to calculate the slope pitching thickness, that is the value of small t. This small t we can calculate small t equal to 0.06 times of q to the power 1 by 3, as we discuss in design steps number 4. Okay, value of small t, capital T and L, as discussed in previous. We have to calculate this all parameter. So for this we use discharge equal to 10,000 and the slope pitching thickness, that is value of small t, becomes 1.3 meter. So we have to provide 1.3 meter side sloping pitching. Okay, so this thickness t equal to 1.3 meter. Okay, so you have to show this value in figure. Okay, this is very important. We have to provide different calculated data over here in this figure. Okay, and in exam you must provide this figure with this different calculated value. Okay, now we have to calculate thickness of Operon, that is value of capital T, this capital T, and this value can be calculated using this formula 1.9 times T, 1.9, and the value of T is taken 1.3. This value becomes 2.5 meter. So we have to provide capital T equal to 2.5 meter. Okay, you have to mention in this figure, and so provide thickness of Operon equal to 2.5 meter. Now we have to calculate length of Operon, that is L equal to 1.5 times of D. Okay, and for this we have different two conditions. As we discussed, the length of Operon can be calculated equal to 1.5 times of D, and the value of D is taken 1.25 r minus y for the state, and D equal to 1.5 r minus y for the curvilinear. So we have these two conditions. Okay, and we have to calculate these two conditions individually. So for state this Grad bank, we have to use this formula D equal to 1.25 r minus y. Okay, and value of y is already known, then that is 8 meter. We have already calculated the value of y equal to 8 meter, as I this. Okay, the value of y equal to 8 meter. So you have to show this value also in the figure. So this value is 8 meter. Okay, so simply say this is the 8 meter, that is the depth of water above the bed level. Okay, and now we can calculate the value of F equal to 1.67 root under D. And what is D? D is the size of silt particle. Okay, and the size of silt particle in given question equal to 0.25 meter. Okay, so we just use this value 0.25 meter. So the silt factor Fe becomes 0.88 meter. Now we have to calculate the value of 0.47 root under Q by F to the power 1 by 3. And Q is already 0.88 after calculating this value. Okay, and this value gets 10.56 meter. And now we have to calculate D equal to 1.25. Okay, then we get the value of D equal to 5.2 meter, and length of Operon L equal to 1.5 D, and D is taken 5.2 meter. This becomes 7.8 meter. Okay, so you have to write here this is the length of Operon, and this becomes 7.8 meter. Okay, this is for the length of Operon for the state this Grad bank. Okay, now let's see whenever for the curvilinear transition portion of Grad bank. Okay, and now we have to calculate this value, that is 11.76. You have to show in next figure. Okay, this figure is for the state this Grad bank, and for the curvilinear transition we have to make same this figure in another. Okay, so you have to make two different figure. Okay, but for now I will show these two value in this figure. Okay, and after calculating d equal to 1.5 r minus y, r is the value is 10.56 minus y is 8. This value becomes 7.864. okay, only the value of d is changes. Okay, in above this value is 5.2 and in this this value is 7.86, and we can calculate length of apron L equal to 1.5d, and we use this value, so the length of apron becomes 11.76. so length of apron becomes 11.76. okay, so we have to provide this two different value into different figure. Okay, provided in this figure. Okay, but you have to provide into different figure. Okay, so this is of Grad bank, or you can say okay, so this is all about this numerical. Okay, thank you very much. See you in next video. If you like the video, please do subscribe the channel and like the video. Thank you very much. See you in next video.